anyhow, welcome everybody from all over the world to you and to your students and to your viewing parties. We are really excited today to have Peter Cameron joining us. He got his BSc from the University of Queensland, a DPhil from Oxford. Spent most of his career at Oxford, Queen Mary, London, but he's currently at St. Andrews as a half-time professor. He's got a long and impressive career, both the junior and senior Whitehead prizes from the London Mathematical Society, the latter just recently, and ICA's Euler Medal in 2004. He's the chair of the British Combinatorial Committee since basically forever. And he is a serious marathon man, both mathematically with some 300 or more publications and 200 co-authors, and genuinely as a marathon man. He's an Australian University's cross-country champion with a best marathon time, and I'm impressed, Peter, my goodness, of 2 hours, 46 minutes, and 59 seconds. Take the talk a little slower. Okay? But
Right.
We're very, very happy to have you. And Peter's going to tell us about 4 precious jewels today.
Thank you very much, Joe, and thank you everybody for coming along to watch. Now, I should start off by saying I've never done anything like this before. I'm used to talking to an audience where I can see where you're getting bored or nodding off, and I can't do that. So if you feel absolutely the necessity to butt in, please butt in. Okay, so I'm going to be talking about 4 really amazing things. The first one is the random graph, the countable random graph, which is actually one of my party pieces. And apologies to the folks in Worcester who heard this not so very long ago. So I'm going to be telling some of the same story again. Next is the rational numbers as ordered set, which is something we've all known about for a long time, but it fits into the same framework as the random graph. The Urysohn metric space. This was a little bit of a surprise when I learned about this. I was talking about the random graph at the European Mathematical Congress in 2000, and Anatoly Vershik was there in the audience, and he came up to me afterwards and said, "Do you know about the Urysohn metric space?" And I said, "No." And so he told me, and it's a beautiful story as well. And finally, something called the pseudo-arc that I only learned about a couple of years ago. And it's a little different. If we run out of time, I'm afraid the pseudo-arc is the one that will get ditched, but we'll just see how we go. So those are the things that I'm going to be talking about. And the reason I'm talking about them to a combinatorics seminar is that they don't look like, well, the random graph looks like combinatorics. The other things perhaps don't, but they can all be constructed and studied by the methods of finite combinatorics, so we can make some contribution to the study of these beautiful objects. And not only that, but the things that led to these have fed back into Ramsey theory and also topological dynamics and other areas. And I'll try and say a bit about all of these things as we go along. So, first of all, random graphs. Well, in 1963, Edesh and Renyi published quite a long paper on asymmetric graphs. So they showed, as is absolutely common knowledge now, that a typical graph, a typical finite graph, not only has no non-trivial symmetry, but it's as far as it can be, in a certain sense, from symmetry. Given a graph, you can change a certain number of edges to make it have some symmetry, and most graphs lie at essentially the maximum distance from symmetry. So things that we know and love, like the Peterson graph, are actually very rare, and perhaps all the more precious for that. But in the same paper, in a little note at the end, Edesh and Renyi showed that for countably infinite graphs, the situation is very much different. They showed in that paper that such a graph with probability 1 has infinitely many automorphisms. So although the probability of having an automorphism is tending very rapidly to zero as you go up through finite graphs, suddenly when you hit the infinite, it's different, and they're highly symmetric. And in fact, they didn't say so in that paper. I'm not quite sure when they figured this out, but the true reason is there is only one countably infinite random graph. And I'll show you the proof of this. And I'm fond of saying that no other subject than mathematics has the ability that I can convince you of such an outrageous claim in 5 minutes, and you'll be absolutely certain that I'm right. If I tried to do this in history or chemistry or anything, you just go away thinking that I was crazy or something. But anyway, I'll prove to you that there is only one countably infinite random graph, and it's highly symmetric and has many properties and arises in many different parts of mathematics. So let's switch to Richard Rado, who in 1964, the year after the Erdős-Rényi paper, and I don't believe that he was aware of what they were doing or that they were aware what he was doing. He published a construction of a particular countable universal graph. By universal, he meant that every finite or countable graph occurs as an induced subgraph of this graph. So he gave it an explicit construction of such a graph. Oops. So he just constructed it. He didn't say anything about whether it was unique, whether it had symmetry or anything like that. And the construction is very simple. Here it is. The vertex set is a set of natural numbers in which I include 0. And I've got to tell you when to join two natural numbers, x and y. One of them is smaller. Let's suppose x is smaller. So I write y in base 2, and I look to see whether the x digit is equal to 1. If it is, I join. If not, I don't. So, for example, oh, I thought I had an example coming up. I don't. Never mind. For example, 0 is joined to every number that has a 1 in the units position. That is every odd number. 1 is joined to 0 because it's odd, but it's also joined to every number that has 1 in the 2's position, so numbers congruent to 2 or 3 mod 4. Anyway, to proceed, here's another graph. Doesn't look anything like Rado's graph. You take the primes congruent to 1 mod 4. You join P to Q if P is a quadratic residue mod Q, or P is congruent to a square mod Q. And here's another example. If you're into set theory, take the Zermelo-Fraenkel axioms of set theory. If they're consistent, as we all hope, then according to a theorem called the Löwenheim-Skolem theorem, they have a countable model. What's a model of set theory? Well, it's got a bunch of things called sets, and it's got a membership relation. A set can belong to another set. So a model of set theory is really just a directed graph satisfying a whole lot of very strange conditions. But I just simply undirect the graph. I say x is joined to y if either x belongs to y or y belongs to x. So there are two apparently quite different graphs, and apparently both quite different from Rado's graph. They are actually isomorphic to it, and I'm going to show you why. It is the random graph. Right, so here's the proof that the random graph is unique and highly symmetric. So we use something called the Alice's Restaurant property. Those of you old enough might remember the song, "You can get anything you want at Alice's Restaurant." Anyway, anything you want means that if you take any two finite disjoint sets of vertices in the graph, you can find a vertex that is joined to everything in U and nothing in V. That is, given a finite set of vertices, you tell the waiter which adjacencies and non-adjacencies you want, and the waiter brings you a vertex Z that has the correct joins. Right, so here it is in a picture. U and V, two finite disjoint sets of vertices. There is a vertex joined to all of those guys and none of those. Now, of course, an arbitrary graph may or may not have that property, but let's see what it means for a graph to have that property. So basically it says if I have any finite subgraph of R, every possible extension of it to one more vertex occurs. And so inductively you can see that a graph with this property is going to contain every finite graph, and indeed every countably infinite graph, as an induced subgraph just by induction. So it's clearly quite a strong property. But let's dig a bit further. How likely is this property to hold? Well, we use a little bit of measure theory here. A countable union of null sets is null. So there are countably many choices of the sets U and V. And for each choice of U and V, if I could show that the probability that the vertex Z exists was 1, that would say that a particular U and V failing this test would be a null set. And since there are only countably many, that would say the whole property star failing would be a null set. So why is it true that given U and V, such a vertex exists? Essentially because if n is the number of vertices in U and V together, pick a vertex. Probably it doesn't have the correct joins. It's not the one you ordered, you'll have to send it back. The probability that it's not the one you ordered is 1 minus 1 over 2 to the n. But if that one doesn't work, the waiter brings out another one, and that's independent of the first one because we chose the edges independently. So now the probability that neither of these two work is 1 minus 1 over n squared. And you can go on doing that as long as you like, and you see that the probability of not getting such a vertex goes to 0. So condition failing for this particular choice of U and V is a null set, and so we've proved the property star holds in the random countable graph. So now what do we do? Well, any embedding of a finite graph into R can be extended to one further vertex in all possible ways, so it's universal. And now there's a wonderful gadget called the back and forth argument that shows that any two graphs with this property are isomorphic. And I'll show you in a picture why that's true. Imagine that you have two countable graphs, both satisfying property star. So I enumerate the vertices of the first one along that line, and I enumerate the vertices of the second one along that line. And I want to build an isomorphism between them, given that they both satisfy condition star. So I start off, I might as well map A0 to B0. There's nothing to stop me doing that. And then, suppose I'm at an even numbered stage. I've already mapped some of the vertices upstairs into vertices downstairs. So I choose the first vertex that I haven't yet applied the map to. Let's suppose it's AM. So AM is the first unmapped vertex. It's joined to some of the mapped vertices and not joined to the rest. So let's call those sets U primed and V primed. Now, U primed and V primed have already, we know how to map them across into this other graph, so we map them across and call the image sets U and V. Now, condition star says I can find a vertex in here somewhere that's joined to everything in U and nothing in V. And that vertex will be suitable as a target for extending the isomorphism to map AM to this new vertex that we've just found, like that, right? So I do that at even numbered stages. I can't just do that all the way through. It looks very tempting, but if I did that, there might be vertices down here which would simply never get hit. So I have to, at odd numbered stages, go back the other way, choose the first vertex that I haven't hit yet on the bottom layer, and reverse the procedure to find a pre-image for it in the top layer. So if I go on doing that, eventually I will have run through all the vertices at the top and mapped them all across, and every vertex at the bottom will have got hit, and so I will have built an isomorphism. So condition star, there is a unique graph satisfying it. Well, we don't quite know that yet. We know that there couldn't be two non-isomorphic graphs satisfying it. Why is there one at all? Well, we know it holds with probability 1, and if something holds with probability 1, it certainly holds. So there is a graph with the property. So it's a classic non-constructive existence proof that such a graph exists. But there is already a construction, there's Radau's construction. So in order to show that Radau's construction or the quadratic residue construction or the Zermelo-Fraenkel construction give isomorphic graphs, you simply have to verify that they all satisfy the Alice's restaurant property. For Radau's construction, this is quite easy, I'll leave it as an exercise. Let's take the number theory construction. Remember, we took the primes congruent to 1 mod 4, and we joined P to Q if P was a square mod Q. Now, the law of quadratic reciprocity shows that if P is a square mod Q, and they're both congruent to 1 mod 4, then Q is a square mod P. So this really is an undirected graph. And then using a little bit of Chinese remainder theorem and Dirichlet's theorem, you find that the Alice's restaurant condition holds. For the set theory construction, you need just a few of the axioms, and again, you can verify that the property holds. So all of these graphs are isomorphic. Not only that, there are a couple more properties. We saw already that a graph with property star is universal. Here's the property that says it has a lot of symmetry. A structure is homogeneous if whenever you have an isomorphism between finite pieces of this structure, you can extend them to an automorphism of the whole graph. In other words, you can extend this mapping between the finite structures so that it works on the whole graph and bijectively maps the whole graph to itself. So the random graph is homogeneous. And how do we prove that? Well, go back to the back and forth argument that we had back here. This. We started off just mapping the first vertex to the first vertex. But I could have started with any initial data. I could have started with an isomorphism between a finite amount of stuff at the top and a finite amount of stuff at the bottom, and then just run the back and forth machine, and it will build you an isomorphism between the two graphs, which extends that finite isomorphism. So the back and forth proof says if you give me an isomorphism between finite subgraphs, you can extend it to one additional point, you can extend its inverse, so you can extend the whole thing to an automorphism of the graph. So a graph with this property, the Alice's restaurant property, is homogeneous. And as a consequence, the thing that Edesh and Rainey noticed, that it has infinitely many automorphisms, must be true, because there are infinitely many vertices. Mapping any one to any other is a finite isomorphism, so that can be extended to an automorphism, and all these automorphisms are different. And there's a lot of work now on the group of automorphisms and the semi-group of endomorphisms of R, but that's not what I'm going to talk about now. That was a quick whistle-stop tour through the random graph. Now let's go to the second topic, the rational numbers. So the rational numbers just as ordered set. I forget the arithmetic and just have the order on the rationals. And the famous theorem of Cantor in the late 19th century says that if you have a countable ordered set which is dense, that means between any 2 points in the set you can find another point, and there's no least or greatest element, then it must be order isomorphic. Isomorphic is ordered set to the rationals. So the rationals are the unique countable dense linear order without endpoints. So how do you show they're homogeneous? Well, you can actually show how to extend a finite isomorphism like this. Suppose I give you, let's say, 4 rationals and another 4. I want to find an order-preserving map that takes the first 4 to the second 4. Well, there's only one order that I can map them in. Now I've got to preserve the order. So I'm stuck with that amount of the structure, but then I can fill in these gaps. This gap here, I just shrink it down so that it'll fit in that gap. This gap here, I stretch it a bit. This one, I just move back a bit, and so on. So, but with a piecewise linear map, you can extend this given data to an order isomorphism of the whole set of rationals. that shows that it's homogeneous. So this shows that the rational numbers form a homogeneous total order. Universal, well, the only finite total orders are the usual order on the first n natural numbers. And of course, that by definition is embedded in Q. So it is universal as well. So this example of a universal homogeneous structure was known well before Erdős and Rényi started thinking about graphs with this property. So the person who'd been thinking about it, though, was Roland Fraisse, French logician. Well, his subject really is what you might call the theory of relations. And in a sense, he more or less single-handedly invented the theory of relations and invented a lot of very cute terminology to describe it, some of which I'll mention in a moment. So a graph is an example of what Fraisse would call a relation. I would probably call it a relational structure. It's just a set with some relation or perhaps several relations on it. So a totally ordered set is another example. So in logical terms, we have a first-order relational language, only relations, no functions or constants, and graphs and total orders are examples. So when I have such a structure, and I have two structures, I have a map between them, it's going to be an isomorphism of induced substructures. If I map A to B, every instance of the relation in A must be carried to an instance of the relation in B, and every non-instance must go to a non-instance. So if you think about graphs, that says every edge must go to an edge, every non-edge must go to a non-edge. So this is just saying isomorphism of induced subgraphs. That's the best way to think about it. So we're going to think about maps like that. And I will allow the empty set as a structure. There's a unique structure on the empty set. This just makes some of the definitions later a bit easier. I don't want to get into empty set theory too much. So Fraisse's term, the age of a relation or relational structure, is the class of all finite structures which can be embedded into A. So the age of a countable universal graph is the class of all finite graphs, for example. And once Fraisse had introduced this term, the age, he could talk about one relation being younger than another if its age was contained in the age of the second relation. And he had a notion of a rich relation and various other linguistic tricks. But the age is all that we're going to need. So the age is the class of structures embeddable in A. So a class A is called hereditary if it's closed under taking substructures. And the crucial property is the amalgamation property. The amalgamation property says, if I have two structures in the class and they have bits that are isomorphic, I can pick up one and I can glue it together according to that isomorphism to get another structure in the class. So for example, if I have a copy of A in B1, copy of A in B2, I can pick up this copy of B1, put it down so that A coincides, perhaps a little bit more coincides, I don't mind, and perhaps there are things outside this union, I don't mind about that either. Just simply, I can do something like that. That's the amalgamation property. So that's a property of a class of finite structures. And in terms of these things, Fraisse was able to give a complete characterization of when universal homogeneous structures exist. So this is his theorem. He says a class of finite structures is the age of a countable homogeneous relational structure if and only if it's closed under isomorphism. Well, that must be the case because if two structures are isomorphic and one can be embedded, so can the other. It's got to be hereditary for similar easy reasons. It should have only countably many members up to isomorphism because we're trying to pack them all inside a countable structure, so there can't be more than countably many of them. And the crucial thing is it must have the amalgamation property. So the age of a countable homogeneous structure has all these properties. So we've seen two examples so far. We've seen the random graph, we've seen the rationals as ordered set, and in each case it's countable and homogeneous, and we observed that the age has some of these properties. If you take the amalgamation property, how do you amalgamate two graphs? Well, you just stick them together. It doesn't matter what edges and non-edges you put in the bits outside the part that you're amalgamating. But there's more to it. If these conditions hold, then the countable homogeneous structure with AJ is unique up to isomorphism. So this says there is a unique countable homogeneous universal graph, and that's the random graph. So that's why it crops up all over the place, because it's the only one that has these beautiful properties. So nowadays we call a class of finite structures satisfying these conditions a Fraisse class, and the countable homogeneous structure is its Fraisse limit. So finite graphs form a Fraisse class, and their Fraisse limit is the random graph. Finite total orders form a Fraisse class, and their Fraisse limit is the order on the rational numbers. And then you can go back and look at the Alice's restaurant property of the Fraisse limit, and that says that if B and C are elements in the age, and B is contained in C, with C having one more thing than B, then any embedding of B into M extends to an embedding of C. That's exactly the Alice's restaurant property for graphs that we had earlier on. So that's the condition that that Fraisse used to build the countable structure, and everything works just as it did for the random graph. So this was Fraisse in the late 1940s, so some time before Ehrlich and Ramsey came along and did it for graphs. So this is reverse history in a way. So here are some more examples. As I said, the Fraisse limit of the class of finite graphs is Rado's graph, or the random graph if you like. The class of triangle-free graphs has all these properties. Amalgamation for triangle-free graphs don't put in any extra edges except the ones that are there in the things you're amalgamating, and if you don't, you won't create any triangles that weren't there before. There is a unique graph, countable homogeneous graph, that's Henson's graph. So Henson found this around 1970. Bipartite graphs don't form a Fraisse class. If you think about the path of length 2 and the path of length 3 and try joining them at the ends, you'll get a 5 cycle, even though they're both bipartite. But if you specify the bipartition, you wouldn't be able to do that amalgamation, because the two ends of the path of length 2 should be in the same class, whereas the two ends of the path of length 3 should be in different classes. So graphs with bipartition form a Fraisse class, and there is a generic bipartite graph. Total orders, the rationals. Partial orders, there's something called the generic poset, and permutation patterns. This is well, more than just a cottage industry. It's a nice little area of combinatorics with some really beautiful stuff. Permutation patterns is the study of the age of two independent total orders on a countable set, which makes something called the generic permutation. So quite a lot of combinatorics fits into this pattern. And as I say, there are many, many others. Right, so let's roll the history back a little bit further. So this is Pavel Urysohn. If you've studied any topology, you've certainly come across Urysohn's lemma and various other things that he did. But one thing he did was anticipate Fraisse and Ehrlich and Ramsey, as I'll show you. And this is the story that Vershik told me at that meeting in Barcelona in 2000. So, Urysohn, it's a tragic story. He came to Western Europe with Alexandrov. He met up with Brouwer and Hilbert and various other people, including, I believe, Hausdorff, went on holiday to the south of France, went swimming in the sea during a thunderstorm and was drowned. And what I'm going to talk about had not at that point been published, so Alexandrov and Brouwer had to write it up from Urysohn's notes it was published in, I think, 1924. So anyway, this is Urysohn's last theorem, in a sense. So I need a little bit of terminology that you may well not be familiar with. So a Polish space is something like the real numbers, a complete separable metric space. Complete means Cauchy sequences converge. Separable means there's a countable dense subset, like the rational numbers inside the real numbers. And what Urysohn showed, this was an answer to a question that was asked by, I forget which topologist at the time, is there a universal metric space? Well, he showed that there's a universal homogeneous Polish space. In other words, a complete separable metric space contains every finite metric space, and every isometry between finite subsets extends to an isometry of the whole space. So this is metric spaces, so the structure-preserving maps are isometries, are distance-preserving. So Urysohn proved the existence of a universal homogeneous Polish space. And to do that, he essentially had to invent the technology that Fraisse later developed in greater generality. So I'm going to not go back to the way that Urysohn did it, but I'm going to pretend that we have Fraisse's technology available and just see how that would give you the construction. So first of all, your first thought about it was look at the class of finite metric spaces. Unfortunately, it's not a Fraisse class because there are too many. Just look at the two-element metric spaces. They're determined up to isometry just by the distance between the 2 points. That's any positive real number, so there are uncountably many of them. We can't cram them all into a countable metric space. So we have to do something different, and this is what essentially Urysohn did. He said, let's restrict to rational metric spaces, ones with all the distances rational. There are only countably many of those. It's an exercise to show that it really is a Fraisse class. As usual, the amalgamation property is the thing that requires a bit of proof. So it's a Fraisse class. Take its Fraisse limit. That is a countable universal homogeneous rational metric space. So it's not a Polish space, but we can take its completion, just do the usual thing that you do to get from the rationals to the reals, make the Cauchy sequence, add limits for the Cauchy sequences. So take the completion, then you still have to do a little bit of work to prove that the completion is now a countable universal metric space. Indeed it is. That's the Urysohn space. Well, there are a couple of other examples we could do. Suppose we, instead of starting with rational metric spaces, we started with integral metric spaces. Then everything goes in the same way, except we no longer have to take the completion because if all the distances are integers, Cauchy sequences are eventually constant, and so they definitely converge. So once we've built the integral metric space, the job is done. It's a kind of homogeneous distance transitive graph, if you like to put it in those terminology. Well, more than distance transitive. Distance transitive says if I take two pairs of vertices at the same distance, there's an automorphism that carries one to the other. But we can do it not just for pairs, but for n tuples of vertices. For any n, if two n tuples are isometric, then there's an isometry, there's an automorphism of the whole graph that maps one to the others. But what if we just use the distances 1 and 2? Then we get the random graph, because a metric space with distances 1 or 2, let's make a graph out of it by joining two vertices if they're at distance 1, not if they're at distance 2. And if it's the Fraisse limit of this distance 1 and 2 metric space, then it's easy to see that the graph distance coincides with the metric space distance. And so saying that it's a universal homogeneous metric space with distances 1 and 2 is exactly saying it's a universal homogeneous graph. So it's the random graph. So Urysohn could have constructed the random graph had he been interested in doing that. Anyway, so that's the Urysohn space. And So what good are all these things? Well, I want to talk a little bit about some things related to homogeneous structures. First of all, Ramsey's theorem. In this century, there's been quite a remarkable development connecting homogeneous structures, Ramsey classes of finite structures, and topological dynamics. So let me just say a little bit about this. So here's Ramsey's theorem, which you may probably have seen before. So we're given integers k, l, and r, k less than l. Then there's an integer capital N such that if you color the k element subsets of a set of that size with r different colors, you can find an L set, all of whose k subsets have the same color, a monochromatic L set. So that's the numerical Ramsey's theorem, which goes back to Ramsey in the 1920s. But this has been widely generalized. So we want to generalize it from a theorem about sets and cardinalities of sets to a theorem about structures, such as graphs. So to make things convenient, instead of saying subset, we're going to say embedding. So if A and B are structures, I'll let B choose A be the set of all embeddings of A into B. Maybe it's not a very good notation, but let's just stick with it for the time being. So B choose A is the set of embeddings of A into B. Now we can turn Ramsey's theorem into a definition. We say the class of finite structures is a Ramsey class if, given any A and B in the class and a number R greater than 1, there is a structure C in the class, so that if you color the A element, the embeddings of elements of copies of A into C, so this is basically the copies of C isomorphic to A, except that, as I said, we're actually using the embeddings instead of the copies. So if you color the embeddings of A into C with R colors, then you can find an embedding of B into C such that all of the copies of A that lie in B get the same color. So that's a structural definition. A Ramsey class is a class of things that have that property. And it turns out there's a technical reason why, once we leave the realm of sets and go into structures, we have to assume that all the structures in A have trivial automorphism group. And the easiest way to achieve that is to think of them as labeled structures. In combinatorial enumeration, we can count labeled or unlabeled structures. Labeled structures just means the vertices are numbered 1 up to n, and the isomorphism is supposed to preserve the numbering. And it's clear that there aren't any automorphisms because you can't commute the numbers 1 to n without destroying their order. So that's, we'll use labeled structures from now on. Well, Jarek Neshatril observed that if you have a hereditary class which happens to be a Ramsey class, then it must actually be a Fraisse class, and so it has a Fraisse limit. So labeled graphs form a Fraisse class, and what's the Fraisse limit of labeled graphs? Well, the Fraisse limit of graphs is the random graph. The Fraisse limit of totally ordered sets is the rationals. So it's basically the random graph with the vertices indexed by rationals in a way that's completely independent of the graph structure. And so anyway, once Jarek had observed that, he suggested that if we want to find all the Ramsey classes, what we should do is determine the homogeneous structures, find their ages, and check the Ramsey property for the ages. And that looked promising at the time, because this was at the time of the work of Laughlin and Woodrow characterizing the homogeneous graphs, and then Churlin went on to do the homogeneous tournaments and digraphs. So it looked like this was a feasible program. And several Fraisse classes of labeled finite objects turned up to be Ramsey classes. And some of the ones we've met, graphs, triangle-free graphs, permutations, metric spaces, are all examples of Ramsey classes. Now, a small detour into topology. If you have the symmetric group on a countable set, there's a natural way of giving it a topology. Now, topology is basically a way of saying when two things are close together. So two permutations are close together. If they agree on a long initial segment of the natural numbers, you've got to go a long way out before you find that G and H really are different. So you can define a metric using that intuition, and this puts a topology on the symmetric group. And I just want to quote a couple of facts about it. It comes from a metric, as I said. The group is complete with respect to that metric. A subgroup is closed if and only if it's the automorphism group of something, which is rather cute. And the something can be taken to be a relational structure. So the closed subgroups of the symmetric group are automorphism groups of relational structures. And because they're closed subsets of a complete metric space, they are themselves complete metric spaces. So in fact, they're complete metric spaces in their own right. Right, now, this was the real, to me, the real bombshell. There's a concept in topological dynamics. A group is said to be extremely amenable if, whenever it has a continuous action on a compact Hausdorff space, it must fix a point. Now, you may know people who work on amenability. This is, as far as I know, the strongest form of amenability you can have. And there were some examples known, but Kechris-Pestov and Todorcevic came up with this remarkable theorem which gives us a big stock of extremely amenable groups. They said, if you have a Fraisse class with Fraisse limit M, the following conditions are equivalent. First, that A is a Ramsey class. Secondly, that the automorphism group is extremely amenable. Now, this just seems, on the face of it, so unlikely, but that's the theorem. So any Ramsey class which has the amalgamation property will give you an example of an extremely amenable group. So we have got something to say to the topologists after all, you see. Anyway, I said that in a Ramsey class the structures must be rigid, and I didn't explain why, but you can make them rigid by including a linear order in the language. So in other words, by considering labeled structures. Now, using the KPT theorem, we can see why. Suppose that you have a Fraisse class, M is its Fraisse limit, and then you look at all the linear orders of M, then you can make them into a compact Hausdorff space, and the automorphism group of M clearly acts on that. So if the group is extremely amenable, one of these linear orders must be fixed by the automorphism group. So the structure has in it a linear order, either explicitly or somehow defined by the rest of the structure. So Ramsey classes have to have a linear order built in, so that it explains that. Right, good. Then I have time to tell you about the pseudo-arc. So this is something a little different, but it was a question that came up in topology in the first half of the 20th century. What does a typical closed connected subset of the unit square look like? Now, let's just step back a minute. What does a typical closed connected subset of the unit interval look like? Well, that's easy. If it's closed and connected, it must be a closed interval. And all closed intervals are essentially the same to a topologist. They're all homeomorphic. So there's only one type of closed connected subset of the unit interval. But how about the unit square? That seems to be much more freedom in choosing a subset of the unit square. But we have to wonder about what this word typical means, because obviously there are lots of subsets of the unit square which won't look anything like one another. And when I talked about the random graph, typical was a set of measure 1. So the random graph is the typical countable graph in that sense. But here, we're doing topology, so we don't have a natural way of saying choose at random. So we use something, we use a notion from Bayer category instead. So this applies in a complete metric space, which we need to build one, but I'll come back to that. In a complete metric space, a set is residual if it contains a countable intersection of open dense sets. And residual sets are large sets in a similar way that complements of null sets are large sets. we say that almost everything has a certain property if the complement is a null set. Well, topologists say almost everything has some property if it forms a residual set. And so residual sets are non-empty. They meet every open set. Any two, or indeed any countably many of them, intersect in a residual set. So they have the property you would expect of typical structures look like this. So now we need a complete metric space. So we go back to Hausdorff again. Hausdorff says, if you have two closed subsets of say, the unit square, how far apart are they? Well, if every point of one is within distance epsilon from some point of the other, both ways round, then we say that the distance between the two sets is less than or equal to epsilon. So we take the smallest epsilon that works, and that's the distance between the two sets. So if they nearly coincide with one another, then they have small distance. But if one is at the top left corner of the square and the other is at the bottom right corner of the square, they might be quite a long distance apart. So that's a metric, and you can show that it's on the set of closed subsets of the square that that metric is complete. So we can use the term residual. We can talk about a set of closed subsets being residual. So a typical closed connected subset will be one member of a residual class. Okay, now, this is the amazing thing. It turns out there is a space P, so that if you look in the closed connected subsets of the unit square with the Hausdorff metric, the ones homeomorphic to P form a residual set. In other words, almost all closed connected subsets of the unit square are the same as P to a topologist. A topologist would say they're homeomorphic to P, so they're the same. So there is only one closed connected subset of the unit square if you're prepared to throw away a few non-typical examples. So that's pretty remarkable, but and so this space P is called the pseudo-arc. And several different constructions were given. R.H. Bing, the Texas topologist, showed that they all give the same object, they're all homeomorphic, and the homeomorphism group of P acts transitively on its points. Well, that last bit won't come as a surprise to us because beautiful objects have large groups of symmetries, and so we would expect that. But there is a bit of a puzzle here, which I will come back to. He showed that this group acts transitively on the points. And here's something else. We were talking about subsets of the unit square, but we can replace that by the unit hypercube in Euclidean space of any number of dimensions, or even in Hilbert space, in the infinite dimensional space. And the P, the typical closed subset, remains the same. It doesn't depend on the dimension, which is, even more extraordinary. So dimension won't tell these typical sets apart. Anyway, so there is some beautiful topological space called the pseudo-arc. And this is all straight topology, and I'm sorry to have bored you with so much topology. We'll get back to combinatorics in just a moment now. How can I construct this pseudo-arc by combinatorial methods? Well, the trick is you have to think in terms of a completely different kind of mathematician, a category theorist. So a category theorist would look at Fraisse's theorem. Fraisse's theorem says if you have an embedding of A into B and into B1 and A into B2, then you can embed both B1 and B2 into C so that the diagram commutes. So they like commutative diagrams. And a category theorist looking at any kind of diagram of objects and morphisms will say, form the dual, turn all the arrows round. So what does that mean? So you have to replace embeddings by epimorphisms. Now let's just stop and think about epimorphisms. A homomorphism of a graph is a mapping that takes edges to edges. We don't care what it does to non-edges. It might take a non-edge to a non-edge, it might take it to an edge, or it might collapse it to a vertex, but edges must go to edges. And so these are mappings. So embeddings go from small to large. Epimorphisms go from large to small. And they're the ones that we'll be using if we turn the arrows around. And so in Fraisse's theorem, you had to build the countable structure by taking a union or a direct limit. Now we have to take an inverse limit, which is something that algebraists like. They talk about profinite groups and things like that. So we're building profinite combinatorial structures here. And the exact analog of Fraisse's theorem holds. It's called the projective Fraisse theorem. It says that you can write down conditions very similar to the conditions in Fraisse's theorem, and they guarantee the existence of a structure which has an epimorphism onto every finite structure, and the property that if I have two different epimorphisms onto the same finite structure, they're related by an automorphism of the big structure. So everything works the same way if you just imagine you're allowed to simply reverse all those arrows. And there's something else too. The inverse limit of a family of finite sets and maps is, well, the construction is a little complicated, but it's contained in the Cartesian product of finite sets. And a finite set to a topologist is just a rather boring example of a compact set. But they have a theorem called the Tikhonov theorem that says that any product of compact sets, even an infinite product, is, again, compact. It's not discrete anymore. It's, in fact, totally disconnected. So we're talking about things like the Cantor set here. So the structures that we build are going to look a bit like the Cantor set. And this is what Owen and Seletsky did to construct the pseudo-arc. So here's their construction. They start off with the class of reflexive paths. So what's a reflexive path? It's a path, but we make the adjacency matrix, the adjacency relation reflexive by adding a loop at every vertex. So a reflexive path is a path with a loop at every vertex, right? And they show that this is a projective Fraisse class. So it has a projective Fraisse limit. This will be an infinite structure that looks a bit like the Cantor set. Now, just to make a small diversion, suppose that I have the Cantor set. You've probably seen the middle third construction of the Cantor set, but basically you can represent it as the set of infinite 0-1 sequences, and you can think of them as you can think of 0 as being the ternary decimal 0 and 1 as being the ternary decimal 2. This represents the middle third Cantor set. But if you think of these 0-1 sequences as binary sequences, you get the unit interval, except there's a small amount of overlap now, because a binary decimal ending with a string of 1s is the same as one ending with an infinite string of 0s. So we have to make some identifications. So to get from the this thing looking like a Cantor set to an interesting topological object, we have to make some identifications. And what they do is they show that if you look at P, it is a graph. It has isolated vertices and edges with loops only. So it's a rather simple and boring graph, but that means it's an equivalence relation with all equivalence classes of size 1 or 2. So there's a natural equivalence relation. We just identify the points in the equivalence classes of size 2. We glue them together. So keeping the same topology, but just gluing together these equivalence classes of size 2, we get the pseudo-arc. So there's a purely combinatorial construction of the pseudo-arc. And using this, Seletsky and Tsankov were able to give a new proof of Bing's theorem. The pseudo-arc has a transitive homeomorphism group. Well, a transitive homeomorphism group. With the rational numbers, with the random graph, with all those nice structures, we've got not just a transitive group, but an absolutely huge group with all kinds of homogeneity properties. Here, Bing got a transitive homeomorphism group. Seletsky and Tsankov were able to reproduce that and get a transitive homeomorphism group. But really the group should be much larger than that. So there should be much more to say about this. And what I would very much like to do is to say, take this combinatorial definition of the pseudo-arc, find a few more automorphisms of it. It must have a huge amount of symmetry. So use that symmetry, exploit that symmetry somehow to get to the what the homeomorphism group really looks like. So that's it. We've covered all 4 of my topics. I didn't necessarily think I'd get that far, but thank you very much for your attention. Thank you.
Excellent, very much. So folks, feel free to unmute yourselves. We can tell Peter thank you, and then open up for questions. So excellent. So give me a holler if you've got questions for Peter. So we'll give this a minute, Peter. Sometimes it takes a little bit of a little bit of fuss for.
Of course, yes. Given how we were at the start, I can understand.
Yep. No, that's all right. But no, this went very smoothly. Thank you very much for taking the plunge into.
Well, it was a bit of a plunge, but
this format. No, this went very well. Good. So yes, do we have any questions, folks, or how are we doing? So I'm looking down here. All right. Well, I'm going to leave the Zoom open for a while. If people just want to chat or hang out, you're welcome. But otherwise, keep your eyes on your email for the next announcement. For those of you who are more or less in the area, the next NCN event will be Summer Combo, which will be the weekend of July 13th. At least that Saturday, possibly the Saturday and Sunday. We're working on the details now, and we'll keep you posted. Bill, do you have any other announcements?
No. Stay tuned. Go to the Northeast Combinatorics website and see what the next events are, and check out our YouTube channel where all these talks will be posted, including Peter's talk from today. Thanks,
yes,
everybody.
Which I did record. Woo! Yes, and as always, if you have ideas for future speakers, let me and Bill know. We'd love to hear your recommendations. Another excellent one like this. Yeah.
Good job.
Super. Thank you.
Thank you.
Okay, thank you.
So we're all done with questions?
We're just hanging out. If anybody thinks of anything.
Okay.
Yep.
That was
Hey, hello?
Yeah, Seth, what's up?
Hi.
Hi.
This is Seth from Albany, Seth Chaikin. Here's an off-the-wall question.
Okay.
What could you say about applications of these techniques and results to, I don't know how to, shall we say, finite situations, say where you want to perhaps estimate things like the Ramsey numbers? Or I guess a naive way to answer the question would be say if I'm a computer person interested only in finite calculations, how might the way of thinking that these results involve help me?
Well, that's a very good question, and I suspect that you already guessed the answer. Probably they won't help you very much. I mean, just because you know that every finite structure in a certain class is embeddable in some countably infinite structure, you don't necessarily learn anything you didn't know before about the finite structure, right? The finite structures, right? There they all are inside that infinite structure. You don't know how far down you have to go before you find one. So I suspect the answer is for the really hard questions in, let's say, finite Ramsey theory, this is not going to help you very much at all. I think, well, the reason why Nechatrel, who is, you know, one of the big figures of Ramsey theory, why he was interested was because he would like to know what the Ramsey classes of finite structures are. And indeed, it was he who proved that metric spaces have the Ramsey property. You see that that's very closely tied in with the Urysohn space and that whole line of country. So the point is that it might be interesting for structural questions about the whole class, but it's probably unlikely to be interesting for specific questions about specific members of the class.
Oh, okay, cool. Well, so the kind of the glimmer that I had in mind was that, you know, there might be a finite thing that is to some in some sense approximately universal.
Well, yes, indeed there are. So, for example, for graphs, or these pseudo-random graphs like Paley graphs, you take a large prime congruent to one, you join x and y if their difference is a square. This contains all not two, you know, if the prime is p, you can get all the graphs of size up to, I forget what it is, but some fairly slowly growing function of p inside that graph. So that's universal for graphs up to some size, and that has, you know, that's probably more interesting to the infinite people than to the finite, because logicians will say, oh, we have this construction called ultra product. We just take the ultra product of all these finite fields modulo primes and a copy of the random graph. Right? But it may not actually help very much with specific questions. But these graphs do exist, and their study is very important. It's another game, though, I think.
Oh, thank you. Thank you.
Peter, since we're just, can you just flip back your slides a little bit to that extension property?
Sure. Well, I actually, I just seem to have got stuck now. Oh, wait a bit.
Oh, never mind. It's...
I'm sure I can do this. Yeah, I can go up. So the extension property. You mean the Alice's Restaurant? That was somewhere about here. No. Alice's Restaurant property. Is that what you want?
Well, further down.
Further down, right. I don't know why the mouse isn't clicking the slides on, but never mind. Here we go. We can do it this way.
Okay.
Tell me when to stop.
Yeah, right around here, up a little bit. So
this is the rationals.
yes, and this homogeneity.
Yes, so here's Fraisse, and here's his theorem. Somewhere around here you want?
No, I was just sort of thinking about that in with respect to Seth's question.
Well, I mean, there are actually there are some quite hard results finitizing these things. So, for example, if you have a finite graph and you have an isomorphism and you have a collection of isomorphisms between finite subgraphs, you'd like to embed it in a larger finite graph so that all those isomorphisms extend to the graph that you first thought of. And you can do that. There are theorems that say that you can do that. They're not easy. And it's not known for all structures, but for some, like graphs, you can do that. And the reason these things were proved is that they actually tell you something about the infinite structures. They tell you, for example, that the automorphism group of the random graph has certain interesting group theoretic properties. But, you know, they're hard finite questions, but it seems to me they would not have been asked if it hadn't been that there was an application to the infinite things lurking in the background.
Mm-hmm. All right. Well, anyhow, Peter, thank you very much for your time.
Okay, well,
And,
I did actually enjoy that.
huh? No, this was fantastic, and we're always very, very grateful for folks in other time zones who are willing to stay up past their bedtime to do this.
Well, it's not quite past my bedtime. It's only just after 8 here.
Okay.
It's still daylight, in fact.
Yeah, you're pretty far north, aren't you?
All over the globe.
Yep.
Wonderful. Thank you so much.
Excellent.
Okay.
So thank you, everybody. Yes. Thank you very much.
Good night, everyone.
Thank you, Peter.
Appreciation by feedback static.
Yeah, right.